Good morning and welcome to Tech 293 on Thursday, February 25th. The subject of today's class is all about ferrous metals, which means they contain iron. And we'll talk more about that in just a couple of minutes. But before, I did want to say that I really enjoyed seeing everyone when they came in for Lab 4. So we did Lab 4 in 2 days, once about a week ago and then once on Tuesday. About half the class came in on each day. And it was really good to see everyone. You know, I have to admit, as we go into further along in the semester and in the school year, I find that I enjoy the hybrid and in-person sessions more and more because it's just pretty isolating sometimes to make all these videos. Even Zoom calls are kind of isolating. So I really do miss being in the classroom and interacting, you know, in the same room with other people because we're just not getting as much face-to-face interaction nowadays in any aspect of our lives. So I really do appreciate the times when we do have those face-to-face interactions. So I enjoy things like doing the labs in this class because I get to interact with you face-to-face in person. So I really enjoyed that in Lab 4, and I'm sure I will continue to enjoy the labs in this class as we continue to break more and more things and do some more cool stuff in this class. So I hope you enjoy it as much as I do. Quick look at the schedule before we move on. Today is February 25th, and we're going to talk about ferrous metals today. What do we have due coming up? Well, we have Lab 4, that was tensile testing of plastic materials. That is due next Tuesday on March 2nd. And then today we're going to talk about Lab 5, which is tensile testing of woods and metals. And then we're going to do Lab 5 in person on March 2nd. So for Lab 4, obviously I had you come in groups. About half of the groups came a week ago on Thursday and half came on Tuesday. And that was kind of to get oriented to the UTM and get used to the tensile testing process. And now I think that we're all comfortable enough with the tensile testing process that I'm not going to split the groups into 2 days anymore. So for the next couple of labs, Lab 5 and Lab 6, and subsequent labs after that, I think we'll be able to do all of the groups on 1 day. Each group will get about 20 minutes, and that should be plenty of time to accomplish the tensile testing and the compression testing that we do in Lab 6 and so forth. All right, we do have another quiz coming up, not for another week and a half or so, but that quiz 4, is, I'll tell you right now, quiz 4 is all about ferrous metals that we're going to talk about today and tensile testing. Mostly on ferrous metals, but a few questions on tensile testing. So you will actually have all of the material that will be asked about on quiz 4 after today's videos. After you watch the videos that I post today, that's all the material for quiz 4. So you can go ahead and take that whenever you feel ready. All right. I didn't say this yet, but Lab 5 that we will do on March 2nd, that's due on March 11th. All right, so that's pretty much it for the schedule. I think I've said everything important that I needed to say about the schedule. So what are we going to do today? What I'm going to do today is make 3 videos, which is a little bit more than I would normally make. But this is going to be all of the videos for today as well as next time for the next class when we do Lab 5. In a normal semester, what I would usually do about this time of the semester in today's class session, I would normally cover about 3/4 of the material on ferrous metals and then call that a day and then come back the following day and cover the rest of ferrous metals, and that would leave enough time to do Lab 5. But the schedule is all different this semester, so what I'm going to do is go ahead and make 3 videos. I'll probably break the material on ferrous metals into 2 videos. And then the 3rd video today will be about Lab 5, how we're going to do Lab 5. All right, so 3 videos today, which is a little more than usual, but I will not be posting any videos for the next class session. We'll just be doing Lab 5 in the next class session. All right, so today's videos, we'll call it Ferrous Metals 1 and Ferrous Metals 2, and then the instructions for Lab 5. That's our objective for today. All right, so I think we can just about get started talking about ferrous metals. So today in ferrous metals, we're going to talk about how ferrous metals are made, the production process for ferrous metals, and we'll talk about the nomenclature, what we call different types of steel. For example, you might remember, I've probably mentioned in passing different kinds of steel like 1018 steel, 1040 steel, 1080 steel. In Lab 3, we did hardness testing on 1045 steel, right? And at the time, you probably had no idea what 1045 meant, but that actually refers to several things about the composition of the steel, what all is added into the steel. So at the end of today's videos, you should be able to tell me more about what is 1045 steel. What does that tell us about the composition of that steel? And then there are kind of some last things that we'll talk about, some special kinds of steel, like tool steel and stainless steel and cast iron. Those are all just kind of specialty kinds of ferrous metals. So let's go ahead and let's get started talking about ferrous metals. So I'm going to share my screen. Okay, ferrous metals. Let's get started. So what we're going to do in this presentation, first we'll talk about production methods for ferrous metals. And when we talk about ferrous metals, generally speaking, we're talking about steel. Because generally we don't just work with pure iron. Pure iron's not that useful. It's way too soft. So when we talk about ferrous metals, we're talking about different kinds of steel. And there are lots of different kinds of steel. It's a very diverse and widely used and very useful material to manufacture stuff out of. So we're going to talk about the production methods for steel, and we'll talk about the nomenclature for how different kinds of steel are named, like 1018, 1045, and so on and so forth. And we'll talk about different types of steel and some specialty steels, like I mentioned, tool steel, stainless steel. And at the very end, we'll talk about cast iron, which is not a type of steel, but it is another type of ferrous metal that is pretty useful and used pretty often. All right, production methods. We're going to talk about each one of these steps in more detail in this presentation, but I want to give you a broad overview first. So here are the high-level steps in the production of ferrous metals, or basically steel. All right, so first of all, you got to get it out of the ground. And the way you get it out of the ground, you mine it. You mine it, and the way you mine it is you dig up rocks. So the way we get iron out of the ground is by digging up rocks that contain iron. And those rocks are called iron ore. And the material inside that iron ore that we're interested in is iron oxide. Iron oxide is another word for rust, right? Because iron, when it's just out in nature, then it tends to be oxidized by oxygen in the air and in water, and it tends to form a compound called iron oxide. So it's kind of a reddish material, just like rust. And the rocks that we're going to dig out of the ground contain iron oxide. And eventually we want to get rid of the other stuff in the rocks, and we just want to get the iron to work with to turn it into steel. Okay, so we got these rocks that contain iron oxide. Then what we're going to do is we're going to grind it all. We're going to grind it up, and then we're going to put it into the first of 2 furnaces that are involved in the steel production process. And the first furnace is called a blast furnace. Kind of a cool name. And the blast furnace is a very tall smokestack looking type structure. And we're going to react it with a lot of other different chemicals. And what's going to come out at the bottom side, actually, the bottom side of the blast furnace is something called pig iron. The funny name, but that is the intermediate product that we're going to work with, that we're going to use as an input into the second furnace. The second furnace that we're going to deal with in the steel production process is called a steel furnace. So you take the pig iron, and that's the input, one of the inputs, into the steel furnace. And the steel furnace, in that steel furnace, we add some other mix-ins, we add some other additives, we burn off excess carbon, and we turn it into the desired end product, which is steel, with the desired mix-ins or additives that you want to be in your steel. Because it's, like I said, it's not just pure iron. All right, there's carbon and a lot of times some other stuff in there as well. All right, then once we are done with the steel furnace, the output of the steel furnace goes into what's called a continuous casting process, usually. That's usually what it goes out into. And I'll show you a couple of pictures and we'll talk some more about that. It produces these final products. I'll show you pictures of these, either slabs or blooms or billets or rounds are the most common final products out of the steel furnace. And then we form it into the final shape. Oftentimes we roll it. It's a progressive rolling, step by step by step. You roll it into what you want your final product to look like. But it doesn't have to be rolled. It could be forged, which basically means you hit it with a hammer, and that hammer has the right shape that you want, kind of like a mold. So you're hitting it with a mold. That's called a forge, sometimes also called a drop forge. You're hitting it with a lot of force. Or you can draw it, which basically means pulling it through a mold. You pull it through a mold to get your desired finished shape. All right, so normally right now I would show this video, and this video is a nice overview of the steel production process. I think if I recall, it's about 7 or 8 minutes, something like that. So it's not super short. It's not real long either. But I think your experience would be better if I did not show this video right now. I think what would be a better experience for you is if you watch this video right now, ideally. So if you want to, you can pause this video, and then you can't probably click on that link, but I will put that link into the description or into the announcement for today, so you can watch that link. And usually I pretty much show almost the entire length of that video. It's a nice overview of the production process for steel that we're going to talk about in more detail in just a moment. All right, so what you might want to do is pause this video, watch that video, and then come back to this video. And that would probably be the optimal experience for you. All right, but I'm going to go ahead and forge on. Forge, see what I did there? All right. So we're going to keep going on and continue and talk about the steel production process. So first of all, you got to get the iron out of the ground. It's in rocks, kind of like this right here. Here's a chunk of iron ore. Usually it's mined in these big, massive open pit mines that frankly are pretty ugly. It's not a great environmental attribute. You know, it's not a beautiful process to extract iron out of the ground. But it is plentiful. There's lots of iron on Earth. We're not going to run out of iron. We may run out of other things, but we're not going to run out of iron anytime in the even remotely foreseeable future. Anyway, you got to get these rocks out of the ground. The rocks contain iron. You can tell because it looks kind of reddish. And the red is the rust, otherwise known as iron oxide. Whenever I see these pictures, or any picture of like a big open pit mine, I think of going to the Caterpillar Museum. It's on the Riverside in Peoria. Usually I would ask everyone, have you ever been to the Peoria Riverside Caterpillar Museum? It's really cool. It's a nice museum. We've been there a couple of times with my kids. My kids are, again, between the ages of 4 and 13 now. and they always really enjoy it. It's got lots of different equipment there, and the first thing you see when you go into the Caterpillar Museum on the riverfront in Peoria, the first thing you do is you go into the museum, you buy your ticket, and then you go in and you go into the theater. There's a theater where they show you an overview of Caterpillar and the different stuff they make and its history and stuff like that. Anyway, the theater itself is in the back, the bed of one of these ginormous dump trucks, like this right here that looks like a little micro machine or something. That's actually not a standard dump truck. That's one of these massive mining dump trucks that are probably, I mean, seriously, probably 5 or 10 times larger, more massive than your standard dump truck that you see driving around town. And the theater that holds probably 50 people, something like that, that theater is in the bed of one of these dump trucks. So these are truly massive dump trucks, and this is a truly massive operation to get iron ore out of the ground. Then we take that iron ore and we crush it up. It gets crushed, and then we take that and we add it to what's called the blast furnace. This is a process that's also known as smelting, and smelting occurs in the blast furnace. So you can see the iron ore coming in here. Iron ore is the crushed up rock. It's the crushed up rocks. And then we also add a material called coke, which is made from coal, and that's basically for combustion. It's fuel. It's to keep the combustion process going inside the blast furnace. And then also we use limestone. Limestone is another rock. It's also crushed up into a powder. And that's basically to help the chemical reactions proceed inside this blast furnace. All right. So those are your inputs. You need iron ore, obviously. That's what's going to give you your raw material for the iron. You use coke. That's for the combustion process. You use limestone. That's for the chemical reactions that need to occur inside here. And also a whole lot of hot air, because these chemical reactions only happen at really high temperatures. So those are the 4 inputs. You should know those 4 inputs. Once you have those inputs, the material is actually floating down. It's floating down this blast furnace, and there's a lot of chemical reactions that are happening during that blast furnace. So you can see here step 1, step 2, step 3, step 4, step 5. I don't need you to know all of these chemical reactions. This is the chemistry of what's going on, but I'm not going to ask you to know all of the chemical reactions that are going on or balance these equations or anything. I just want you to know the process, what's going on. I want you to know what the inputs are, and I want you to know what the outputs are. So the outputs are a lot of waste gases, which again is not a very environmentally friendly process. I mean, it's necessary if you want to get steel. This is the way to get steel. But it's not a real environmentally friendly process. There's a lot of carbon monoxide and a lot of carbon dioxide and other waste gases as well that come off of this blast furnace. You also get a lot of slag. Slag is kind of what's left over, especially from the limestone. So you get a lot of that limestone. That's what's left over from that, and the excess material that's left over after these chemical reactions. So that slag actually floats on top of the liquid molten iron. Down here, you get slag on top, so you can open in this little spigot. It's not just like a little spigot, but you can get the material that's floating on top. You can scrape that off the top, and that is slag. And sometimes that slag, it does actually have a useful purpose. Sometimes it's mixed into concrete. It's an additive into concrete. And then what we're really after is the iron. It's the molten iron. It's still not real pure. It has a lot of impurities in it, and especially it has a lot of carbon. It has way too much carbon to be useful as steel. And we call this pig iron. This is pig iron, which is a weird name. I'll tell you why it's called that in just a minute. But pig iron is the material of interest that is the end product that is coming out of the blast furnace, and it has about 4 or 5% carbon, which is way too much to be useful. If it has that much carbon, that's even more carbon than cast iron, which itself has a lot of carbon. If it has that much carbon, it's going to be pretty strong, but it's going to be really brittle. So it'll just snap apart. And you don't want to make anything out of that. Pig iron, it's an intermediate product. It's what you get out of the blast furnace. And it's going to be what we put into the second furnace, which is called the steel furnace. All right, and that steel furnace is going to have oxygen and heat applied to it, and it's going to burn off through chemical reactions the excess carbon. So it's going to get the carbon down to a desired amount, which is usually less than 1%, but sometimes could be up to 2%. So why is it called pig iron? This is, I don't know, kind of humorous, I think, that it's called pig iron. And especially why it's called pig iron is kind of humorous, kind of just weird. Just weird. So here's why. So when you get the pig iron out of the blast furnace, if I recall, what it shows in the video that I suggested that you watch, what it shows in the video is that the pig iron goes into what are called torpedo cars. They're railroad cars that basically have a big insulated tank. And so what they do is they actually keep the pig iron molten and hot, really, really hot and liquid. And then they take those torpedo cars and they take that over to the steel furnace, and they just take the liquid molten pig iron and put that directly into the steel furnace. So that's one option. But another option that especially in years past was more common was if you didn't want to take the pig iron as a molten liquid and put it directly into the steel furnace, what was pretty common is to solidify it and cool it down into small ingots. Those ingots were like little bricks. They were, about that big. Nothing real huge. You could pick one up and throw it around, and that was a good way to store the pig iron until you were ready to use it by putting it into the steel furnace and turning it into steel. All right. So why is it called pig iron? It's related to these ingots. All right. So here is the output. This is what you could sometimes could do with pig iron. This was real common in olden days when they made steel. Now it's not quite as common. Now it's more common just to take the molten pig iron and put it directly into the steel furnace. But if you wanted to store the pig iron for a while, it's easier to store it as a solid. So this is what the ingots of pig iron look like, and this is the cooling. This is the cooling process where these little ingots, you can see these little kind of briquettes, they are molten, but they're cooling down. They're in the process of solidifying. So what's kind of funny and kind of weird, frankly, is that somebody at some point in time looked at this type of operation right here, where we're cooling down these briquettes of pig iron, and said, that looks kind of like a mother pig, a sow, with baby piglets all lined up in a row. You see how these things are all kind of lined up in a row, just one, then another, then another? That looks kind of like this. All right, so it's kind of weird, honestly, that somebody thought that. But that's where it gets its name. That's why it's called pig iron. So maybe it should be called piglet iron or something like that. But yeah, if you kind of rotate it and you kind of turn it a little bit, you got the piglets lined up one after the other here, and you got the little briquettes of cooling down iron cooling down right here. And okay, maybe I can kind of see the resemblance, but clearly you had somebody that grew up on a farm working with pigs that is responsible for that name. So that's why it's called pig iron. Okay, then we take our pig iron, whether it's still molten or whether it's in these briquettes that you're adding as a solid to the steel furnace. Regardless, you got your pig iron. That is the input, one of the main inputs into the steel furnace. And in the steel furnace, you are going to burn off or react off the excess carbon, and you're going to add your other desirable additives depending on what you want your final steel product to be. It's real common to have steel with manganese in it, nickel, chromium, molybdenum. All those are really common additives for steel, and they all do something just a little bit different to the final properties of the steel. There's a couple different kinds of steel furnaces, and I'm going to talk about 3 of them. The last 2 are still pretty common. The first one is not. It's just the historical method of making steel. So let's go ahead and talk about that first one first. It's called an open hearth, and basically it's called open because it's exposed to the environment. You do have some doors here. There's usually a door here with a flap that lets hot air in. This needs to be a really hot environment to react with the oxygen and the carbon to get that excess carbon to go away. And then you got your charging door. What this means is you're putting your pig iron briquettes or whatever your raw material is, you're putting it through here, through this charging door. If you want to recycle steel, which is really common, steel is very recyclable. So if you've got your old washing machine or something, I don't know, or your old car chassis made out of steel, either one's made out of steel, you can just take your old car chassis or your old washing machine made out of steel and just throw it on through this door. And then it'll come in here and it'll get melted down, and you can make new steel out of it. All right, so you add hot air, you add your raw material, which is your pig iron, potentially some other material that you're recycling. You add your mix-ins that you are trying to mix in, like your manganese and nickel and chromium, etc. And then after it's done reacting, then you tap it off and you take your output, usually through a continuous casting process that we'll talk about later. But this is not real common anymore, not at all, mainly because of contamination. It's kind of open to the environment, and so it's hard to control the chemical reactions that are taking place. All right, the next one that is still pretty common, it's not the most recent, but it's still pretty common, is called an induction furnace. And so here's the molten steel inside the furnace. When you first look at this and you see the coils around the outside, these are coils around the outside, your first guess is probably a reasonable guess, and that is, okay, this is probably working like a crock pot, right? Where your crock pot, you set it at the beginning of the day, you plug it in, turn it on, you throw your meat or material, your potatoes, whatever you want to put inside there, and then gradually it just gets really hot through resistance heating, right? That's what you might expect of this, but that's actually not the way an induction furnace works. The way an induction furnace works is really cool. If you've taken TEC 240 with me, which some of you have, and some of you are taking it right now with me, then you might remember what the requirements for generator action are, otherwise known as induced voltage. What are the requirements for generator action? Normally I would ask somebody who has taken TEC 240 with me, and hopefully they remember that the requirements for generator action, if you want to induce a voltage in a conductor, and by the way, molten steel is a conductor. If you want to induce a voltage in a conductor, you need to have a conductor, you need to have a magnetic field, and you need to have relative motion between the conductor and the magnetic field, all right? If you have those 3 requirements, then you will induce a voltage in the conductor. What's really cool about this type of design is that you actually have generator action. It works like a generator. Your conductor is the molten steel inside here. You have coils of wire around the outside, and the coils are fed with high-frequency AC electricity. Right? So the voltage is positive, then negative, then positive, then negative, positive, then negative. So it's AC electricity. And what you'll also learn in TEC 240, if you haven't already, is that if you have current flowing through a conductor, you will create a magnetic field, always. Current flowing creates a magnetic field. So if we have current flowing through these wires, then we have a magnetic field. In fact, if we apply AC voltage, that's going positive, then negative, then we have a changing magnetic field, right? Because first we induce a magnetic field in one direction with a positive AC voltage, then we induce a magnetic field in the other direction when the AC voltage is negative. So we're constantly flipping the magnetic fields with this AC voltage applied to these coils. And that changing magnetic field provides the relative motion. The changing magnetic field provides the relative motion between the magnetic field and the conductor. So now I meet the requirements for generator action, so I actually induce a voltage in the molten steel, which is kind of crazy, kind of weird, but it works. So we induce a voltage in the molten steel. If you induce a voltage, you have a voltage, then you're going to get current to flow. And it's that current flowing through the material that actually heats up the steel. Just like current flowing through the wires in a toaster heats up the toaster, right? So if you have current flowing through this molten steel, it actually heats up the molten steel, and it gets it hotter and hotter. All right, so that's basically how it works. That was a lengthy description of how this is working, but I want you to know that. I want you to know how an induction furnace works. All right, so that's how we get the heat that is required in an induction furnace. As you might imagine, this takes a lot of energy, a huge amount of energy. In fact, there are some countries on Earth where steel production accounts for a non-negligible part of their entire energy consumption in their country, like 5 to 10%. That's not uncommon, especially for some of the smaller countries in the world. It's a massive amount of energy required to produce steel in one of these furnaces. This is probably still the most common, although the new ones that are being built are usually not this kind, but this is still a very common type of steel furnace. And it's less energy than the open hearth because it's a little bit more efficient, so it's less energy. But it's like I said, it's a lot of electrical energy consumption. All right, the third kind, and this is the more recent kind. So if you're going to build a new steel furnace, then this is probably the kind you're going to build. It's called an electric arc furnace. And the way this works is you have these three electrodes right here and right here and right here. You apply three-phase AC electricity, so phase A and phase B and phase C. You'll learn more about three-phase AC electricity in TEC 240, but basically it's three different AC waveforms that are offset from each other by 1/3 of a period of the waveform. All right, so that's not terribly important for this, but it is three-phase AC that's applied to these three electrodes. And then, because there's a high voltage applied to these electrodes, there's actually an arc. Like, think like lightning. Lightning is an arc. So there's an arc of electricity that forms between the electrode and the molten material. Here is the molten material down here. So you actually get, once again, you get current to flow through this material because you have the arc flowing. The arc is from one electrode, and then it will go into the material and then into a different electrode. So that's basically how an electric arc furnace works. It creates these electric arcs from these electrodes here to the molten material, and then the current passes through the molten material and to another of the electrodes. All right, so this is a little bit more efficient than the induction furnace, but it still takes a lot of electrical energy, a massive amount of electric energy. Here's just a pretty picture of an electric arc furnace. So it's actually inside here. This would be the arc furnace, or inside here you can see the 3 electrodes, and these electrodes are causing the arc to form between the electrode and the molten material, and that causes current to flow through the molten material, which heats up the molten material. All right, so those are the 3 types of steel furnaces. Once we are done with the steel furnace, so we've added what we want to add, the manganese or the nickel, we've got the carbon down to the level that we want it at, whatever additives you want to add. Once it's done, it's got the right consistency, then it comes out right here. And then the most common way of doing this is called a continuous casting process. So this is the molten steel coming out here, and then it passes through these molds, and it's cooling down gradually as it's passing through these molds. And then once it's into a solid by this point right here, then it goes through a whole series of rollers. And the rollers are continuously reducing the cross-sectional area, or the thickness of the material, into whatever shape or whatever thickness you want it to be at. So you're gonna roll it down to the desired thickness here. So by this point, it's much cooler. It's probably still hot, but it's much cooler than it was when it came out of the steel furnace. And now you can cut it and shape it and mold it into whatever form you want. Blooms tend to be very large chunks. Slabs tend to be smaller and a rectangular shape. Billets tend to be a little bit smaller. And then you can roll it even into sheet metal. In fact, that's actually what it's showing right here. So it's showing a continuous casting process here, and then we're going to roll it into shape. Roll forming is the process here. It goes through a whole bunch of rollers, more even that are shown here. It would probably be hundreds of rollers, and each roller is just making it a little bit thinner, just incrementally thinner. So the rollers are pressing on it, and they're thinning out the material as the material is passing between these rollers. So by the end, down here, you've got a very thin material, which you can then roll up. You can roll up the material, and now it is sheet metal. And now you can take that sheet metal and you can send it off to the various different factories that make anything from washing machines to cars or whatever. Sheet metal is a very, very versatile material used in lots and lots of different industries. And this is basically how it's made right here. All right, here's some different forms that you could get after you finish with the continuous casting process. So blooms are the biggest, billets are slightly smaller squares, slabs are just rectangular in cross-section, or you can actually get it into round. If you have those molds at the beginning, if you have those molds in a round shape, then you'll end up with these cylinders called rounds. All right, I talked about this already a little bit, but roll forming is a really important process. It's not just for sheet metal. It's for all different kinds of I-beams and L-beams and channel beams and railroad ties that are showed right here. Or I guess railroad rail, not ties. The ties are either wood or concrete, but the rails, the railroad rails is actually what's being shown right here. So this is a progressive roll forming process. It might start out with a billet like this, and then maybe a couple dozen roll form stages later, you get to this, and then a few more dozen roll form stages later, you get to this, and then progressively, we're deforming it and deforming it and deforming it, and eventually we get to the desired shape like this. Or we could be shaping it into an I-beam or an L-shaped beam or a channel beam. Lots of different possibilities for roll forming shapes. One thing I would also mention is that as we're deforming this, we're deforming it plastically, right? Remember elastic and plastic deformation? So in order to get this to change shape, obviously we are plastically deforming it from here to here to here to here. So as we're doing that, we are causing those dislocations in the material to move, right? And so what we're going to get is work hardening. Remember we talked about work hardening in the stress strain curve. And in most cases, you'd probably say this is a good thing because it makes the final material a lot stronger. This is a stronger material than this because it's had work hardening done to it. So those dislocations that are going to move have moved. And so now it is a stronger material. Sometimes that can be problematic, however. The work hardening can be problematic because if you make it, if you work harden it, then sometimes you get to a point where you just can't change its shape anymore. And so you need to restore its ductility. And so if you get to that point, it depends on what type of process you're going through. But sometimes there does come a point where you need to restore the material's ductility. At that point, what you need to do is some heat treatment. And heat treatment is something we will talk about in this class, but not for another month or so. So I just want to point out that right now that's a connection to something that we're going to talk about later on in this class. But you should know that we do have work hardening happening in a roll forming process. And oftentimes that's a good thing, but sometimes it can be problematic because if it gets too much work hardening, then you can't change its shape anymore unless before it fails. It's going to break. It's going to rip in half or destroy the part unless you restore its ductility through heat treatment, a certain kind of heat treatment. We'll talk more about that later. Here's a picture of a continuous casting process. You can still see that this material is still red hot. So it's still very, very hot. It's just come out of the steel furnace. And now it's probably going to go through some type of roll forming process. As I mentioned, there are lots of different materials you can make out of steel. These are all products that might result from a steel production facility. These are all final products that might come out of a steel production facility. And these are all raw materials or feedstock that might go into some other process that makes car bodies or that makes washing machines or refrigerators or lots of other different possible different things. Okay, let's talk about steel identification. Let's go ahead and talk about those numbers, the way that we identify steel. All right, so what we're going to do is we're going to break it into the first two numbers of the identifying number and the last two. All right, so let's take 1018 steel since it's given here. All right, first we're going to talk about these first two. The first two numbers refer to what other alloying elements are in there besides carbon. Carbon is assumed. If you have steel, then it's assumed that you have carbon in there, all right? But these first two numbers tell you what else is in there besides carbon, all right? And there's a whole bunch of other options. There are lots of different options. So you have your 10 series, your 11 series, 13 series. You have lots of different types of steel. And all these different types of steel have different alloying elements, which give you slightly different mechanical properties for your steel. I'm not going to ask you to memorize all of these, but I would like you to know from memory these first two, because they're by far the most common, all right? So your 10 series is just your plain carbon steel, which means basically it has nothing else besides iron and carbon. It's allowed to have up to 0.4% manganese. It's allowable. It won't always have it in it, but manganese is just another alloying element that does add some strength and some hardness as well. So it works kind of like carbon, but it doesn't quite have the same magnitude of effect of carbon. So Basically, your 10 series are your plain carbon steel, and for practical purposes, it's just iron and carbon. And that's mainly what we're working with in this class because it's the cheapest. It's the cheapest type of steel that you can get. The other one I want you to know about is called free machining steel. It's your 11 series of steel. And it's designed so that it's easier to machine, easier to cut and drill and weld. So it's just a little bit easier to work with. Plain carbon is pretty easy to work with also, but this is designed to be even easier to work with. And what this includes is up to, actually approximately 0.7% manganese and 0.12% sulfur. And frankly, it's really the sulfur that's added that makes it easier to cut and to drill and to work with. All right, these others are important, but I'm not going to ask you to memorize them. You can always come back to this table and you can look at this table or look it up in any materials specification, steel specification sheet, and you can find this. You'll see some of these down here that have chromium in them. The main purpose of chromium or chrome here or here, or frankly even nickel, they do similar things, is corrosion resistance. So we'll talk about stainless steel in a little bit. These are not stainless steel. Actual stainless steel has way more than 0.4% chromium or even 1% chromium. Stainless steel usually has about 10 or 12% chromium. And that's when you get really good corrosion resistance. But even these, with even 1% chromium, will add quite a bit of corrosion resistance. Okay, the last two digits, so the 1-8, the 18 in 1018, that tells you how much carbon you've got in the steel. And like I said, all types of steel have carbon. It is assumed that you have carbon in your steel. And these last two digits tell you how much carbon, and this is the amount of carbon to the hundredths place of a percent. All right, so 1018 is 0.18% carbon. 1040 steel is 0.40% carbon. 1095 steel is 0.95% carbon. A good question you might ask is, what about steels that have more than 1% carbon? Well then, your identifying number here is going to have 5 digits instead of 4. It's real uncommon. You don't see very many steels that have more than 1% carbon. That's a lot of carbon for a steel, and it would be quite brittle, but it's possible. All right, so you should know that. If I asked you about 1180 steel, you should know what are the alloying elements in 1180 steel, and you should know how much carbon 1180 steel has, for example. Here's some more examples. 1020, so we know that it is plain carbon. And the 20 tells us that it is about 0.20% carbon. Another example, 4340 steel. The 43 tells us that it has nickel and chromium and molybdenum in it. And if you want to know the percentages, you go back to that table I just showed. It'll tell you the percentages of each of those. And the 40, the last two digits, tells you that it's about 0.40% carbon. I think this is a good spot to break up the material, so I think I'll stop this video here, and then we'll pick up where we left off with the remainder of the material on ferrous metals in the second video. And there isn't as much in the second video as there was in the first video. And then in the third video, we'll talk about the instructions for Lab 5. So I'll see you in the next video.